Second approach to say, okay, thermodynamics, string theory, value dynamics, some kind of represented part of time, which is prior to quantum mechanics and the periodic table. It's chemical and it's after the kinematics of the smallest particles in the universe. That's even though we don't reach the base blanket to that point, we know as sound equations, energy and motion equations, which is sound and which stands for emotions, and the third being light. So we have a huge gap. Right, I want to illustrate this huge gap. So one, we don't know, unknown to physics, but we can say it's our perception. And this is the cruel point. This is the etherical. And the archangel derives his name from etherical, Gabriel. And Gabriel himself is only a local resident of a black hole. Black hole galaxy with ether. So. And then second is also unknown, and this is ether particles, which are letters, and so we got one, then we got this, then we got 7, then we got, so this is when someone prostates, or someone prostates like this, and someone sits like this, and then the combination of them, right when they collide. So basically this can be a collision particle, or this. So we don't know this. The particles, there are some theories. Frank Mano, Lucas Saul, they look at the function just distributed in the phase space and correlate this to electromagnetic potentials in terms of this F. And Frank Mano relates Dirac tensor to kinematics of gyrants. It's unknown. Few papers exist. And here we have light, which is partially known. And we have sound, which is partially known. And then we have a gap, which are two theories. Here we have a heat theory, we have movement, heat, attraction. And we have a work theory. And in the work theory we have force. But all in all, we can say that this is part of the string theory. Because due to work, particles arise. But now they are at a different time scheme. Periodic table. And what do? We try to fill the gap between sound, light, and periodic table, maybe work. And this is the way to approach it. So we take the force equation from Newton, plug in a force density, plug in a stress tensor, plug in the stress, the Gaussian theorem, then plugging in the vector components of this tensor, then deriving accordingly, which then creates this whole explanation, which I said in the other episode, the other episode was easy. This is more rigorous. As you can see, it looks more geometric. And I evaluate different terms depending on if the determinant of the integral is differentiable or not. So basically I'm taking the integral as a covariant functional, a cotangent functional, and that's why I'm deriving the line integrals with a contravariant vector. No, tangent vector, and I arrive at these equations. So these components are like cotangent and these are like these components are like contravariant and covariant, but many mix it up. But this is a contravariant vector, and this is a covariant vector. This is a contravariant vector, and these are contravariant components, and contravariant components form like covariant vectors. Covariant components form like contravariant vectors. And you get different terms. What I do here is to manipulate the equation up a certain point. I derive the g vectors and I reinsert 1. And once I reinsert 1, I get more derivatives of g squared, g root. And also I evaluate the deltas because of derivating the line integrals. This may be even a Schwarzschild radius if I look at it. And yeah, this was a more rigorous way, but just that you can see also the simpler approach is very useful. And if any of you knows geometrics, I say so, differential geometry, geometrics, mathematical geometrics would be very helpful and useful. So what we can now do is a different approach, because I always stop my approaches until I get it done. So let's use this formula for the force density. And now let's construct a vector, which is like this, and now define the vector here. I'm using Einstein convention. But I could not use it, so let's write it down. Now, what's the geometrics of having a product, a vector A, which has to be covariant, and this equals the vector F. So, what can we use? This is a question that bothers me a lot. But I want to get it done. This is a contraction. Or I make it with the covariant vector. And this is contravariant. I don't know. It's so confusing. So if we take this covariant, and F covariant, now we take a contravariant vector, which is asymmetric. Now this would be 0. But should be so. Wait a second. if I take this vector, So these are some new, these are some, these are some new cool equations. So basically we are trying to operate different geometric quantities to see if they make any sense in a further perspective. But we just wanted to establish a way to vector product geometrically the force density, the force density from covariant electrodynamics, and this energy density and momentum density tensor from electrodynamics T from covariant electrodynamics. So I wonder how it is done. So if I look here, I mean, it's so frustrating.